Okay, now that we learned about the basics of anomaly detection, let's get into the details. In the upcoming modules, we will talk about different approaches. We will continue where we stopped in the first module, namely with the probabilistic method. We will now talk about anomaly detection via density estimation using the well-known kernel density estimator. So the idea here is to estimate the density of the nominal data, assuming that anomalies will appear in areas of low density. So you might ask, why don't we directly try to fit a mixture model as we've formalized it in the contamination framework? I think we've already discussed the reasons. The fraction of anomalies is often too small to really fit a mixture model. And we also discussed that it might be that the anomaly distribution is not even well defined. But then we are left with the problem that we have anomalies or potentially have anomalies in our data. And that's why we are going to look at robust density estimation procedures. So what is kernel density estimation? It's a non-parametric method of estimating densities, meaning that we're not trying to optimize the parameters to fit the data as well as possible, but we increase the capacity of the model as the number of observations grows. It can represent almost arbitrarily shaped densities, and it does so by spreading a little bit of probability mass around each observation that we have in our data set. And the shape of this little bit of probability mass, this little bump that we create at every data point, is given by the kernel. So on the right side, you can see several examples of kernels, for instance, the Gaussian or the top hat kernel, the linear or cosine kernel, and there are many more other kernels. So what is a kernel function? A kernel function is a function that maps real numbers to real numbers so that it's always positive and that integrates to 1. So basically that it is a probability density function. The parameter h is the bandwidth of the kernel, and this is actually the most crucial parameter. Okay, now let's look at the role of the bandwidth in the kernel density estimate. So now let's take a look at the more general case that we have d-dimensional data. In this case, we define the kernel with a certain parameter and bandwidth h as the following expression. So we basically average over all the different kernels for all the individual observations. Here you basically see what we do is we take the distance of the point in question to the observation and divide it by this bandwidth h, meaning that we basically rescale the dimensions of the kernel. In the lower picture, you can already see that the kernel actually does not do so much. No? Here you see a kernel density estimate created from all the points that are depicted below here with different kinds of kernels. So here we have the dark blue being the Gaussian one, we have the light blue being the top hat one, and you have the Epanechnikov as the orange one. So you can see no matter which kernel we take, we get a very similar density out of that. Basically, the fine structure is determined by the kernel. But however, if you would choose the bandwidth smaller and add more data, we would see that this fine structure generated by the kernel actually starts to vanish. But it's really important to choose the bandwidth in the right way. So in case you wonder that we have chosen a rather simple shape for multidimensional kernels, basically just having them depending on the distance to the individual points. Maybe you have also seen a slightly more general version, which I also would like to sketch out here. In this case, we want to have the kernel to be a symmetric. Multivariate density. And we want to take a covariance matrix. So a matrix H in R to the D times D, which is also symmetric. And positive definite. And in this case, we can basically scale the dimensions not only by a constant, by the same constant for all dimensions, but we can use this covariance matrix to scale the dimensions, which will look like this. In this case, we have kh of x being 1 over the square root of the determinant of h times the kernel, and here we apply h to the minus 1/2 to x. So this is the most general way of defining a kernel density estimate in higher dimensions, which allows us to basically scale the dimensions in the same way as we have done it for the Mahalanobis distance. Okay, you might wonder why we have chosen this simpler shape to work with in our workshop. This will get clear as soon as we will talk about robust density estimates. As I've already mentioned, the bandwidth is the most important parameter for the KDE, since a wrongly adjusted value can lead to either undersmoothing or oversmoothing. The bandwidth is the most important parameter to balance the bias variance trade-off, as you can also see in the image below. In the uppermost image, you basically see the dataset that we've fitted the KDE on, and then you can basically see the result for different bandwidths. So in the first image with the low bandwidth, you can see that we still have a high variance as the individual points do not really connect in the KDE, while as we slowly start to increase the bandwidth, you can clearly see that we end up with something that looks terribly oversmoothed in this case. So it's really important to choose the right bandwidth for your data. So how do we select the bandwidth? So a very common way of doing this is via cross-validation, and one often uses leave-one-out cross-validation in this case. So we will try to maximize the log likelihood of the left-out data by adjusting the bandwidth. So the formula for this is written down here. So basically for every point that we can leave out, we compute the kernel density estimate for them, and then we average over that and try to choose the bandwidth that maximizes this expression. All right, now we've learned about the basics of kernel density estimate. I think that's the right time for an exercise to get more acquainted with the practical sides of this topic. In the first exercise, we are going to have a look at the kernel density estimator, and we try to understand how the behavior is for different kinds of parameters. We've prepared again a very simple data set here, basically a mixture of two Gaussians. You see some samples down below here. So in this exercise, there will be no need to code anything. We've prepared already some code snippets, and you just need to play with the parameters. So please go through the notebook, and then we will meet again with the solution. Okay, so let's see what we had here. We already have seen the data set, and once you went through the exercise, you have probably seen that we've already prepared some code to visualize and to fit the kernel density estimate for you. And then you found basically this little interface here which lets you choose the kernel. Let's stay for now with the Gaussian kernel, and then also the bandwidth. And below you could visualize the result with the density contours over the samples. So the initial value were a Gaussian kernel and the bandwidth of about 5.10. And in the image below, you see that this already gave a rather good fit. However, we can also see what happens if we lower the bandwidth and then run this cell again. Then you see we are definitely undersmoothing now, as we are not able to really get a good density out of that. While if you make the bandwidth really low and then render again, you can see that there are even worse effects happening, because now it really has the highest density kind of merged between the two centers of the distribution, and we get like this ghost center here right in the middle of them. Again, shows you how important the choice of the bandwidth is. So we can also see that the kernel, the choice of the kernel, does not have the same kind of effect. Again, we take this bandwidth of about 5.10 and take a look at the top hat kernel. You can see the top hat kernel is one that has finite support. So at some point, we will also have zero densities far away of the data. But otherwise, you can see that the fit is rather similar to what we've got with the Gaussian kernel. You can see similar things, for instance, for the exponential kernel. Again, whatever kernel we choose, like with the data that we have, we will already get always very similar estimates. But if we change the bandwidth, then our estimates can dramatically change. So this is something that you should definitely keep in mind when you're working with kernel density estimation. In the second exercise, we will use cross-validation in order to determine the optimal bandwidth for our data set. Again, there should be no need to code anything. We've already prepared code snippets so that you can just play with the parameters, define the search space, and so on. And we will meet again after you work through the notebook with the solution. Okay. In this example, we have chosen a slightly more complex data set. In this case, the nominal data takes the approximately sinusoidal shape, and the anomalies are in this non-convex area of the nominal data, basically where the nominal data takes a turn and anomalies fall into the gap. So in this case, it's a bit hard. The anomalies are not really outlying, and we have non-convex shapes of the nominal data. So let's see how kernel density can perform there and what are the best values. So in our case, we have chosen the hyperparameters for the cross-validation to be like all the kernels that we've seen so far, the Gaussian, the top hat, the Espanishnikov, exponential, linear, and cosine. And then you basically just had to pass these parameters to the function that's already defined, which does the cross-validation based on sklearn cross-validation functions. And if you ran that, in our case, we got the best kernel to be the exponential one and the best bandwidth to be 0.1. And here we can see at the ROC and the PR curve that this actually allows us to quite confidently identify anomalies. Here the ROC AUC value is already by 1.0, and you can see that the curve is close to being optimal. Similar picture we see for the PR curve. If you visualize the densities, then in this case, unfortunately, we cannot really see the contours because they are overshadowed by the points, but you can see that the density does definitely not reach into the area where we've placed our anomaly. So again, this shows the flexibility of the kernel density estimate. It's no problem to fit these non-convex shapes, which is often much more challenging if we're taking a parametric approach to fitting densities. In the next exercise, we want to move away from synthetic data and try out the kernel density estimate on a real-world data set as an anomaly detection method. We will use the well-known house prices data set, which contains house prices from the area around Ames in Iowa. We can have a look at the data set. It collects several features like the lot area, the sales price, and the overall condition. Additionally, in the original data set, there's also the neighborhood as a feature. And we want to make an anomaly detection data set out of that. And for that, we are going to assume that we have data only from one particular neighborhood, but certain houses from other neighborhoods accidentally got into our data set, and we try to identify them. So in this case, we prepare the data set by defining the neighborhood that we're actually looking at, which is here the college area. And we mix in some anomalies which actually come from the Wanaka area. Let's have a look at that. Here we have a visualization. Again, the blue dots are the nominal data and the yellow dots are the anomalies. And only by looking at this visually, we can already see that there's quite a distinction between the two neighborhoods in the features that we usually see there. So we would expect that we can rather confidently separate these two if our anomaly detection method works well. So now it was basically repeating the steps that we've done in the previous exercise just for this notebook. So maybe you want to do a little bit of pre-processing, scaling, as you know, might be a good idea. We do that here. But then it's just about defining the search space for the hyperparameter optimization. Again, we can take the kernels and we can choose, for instance, the bandwidth in the same bounds that we've looked at before. So now running this thing, we get again that the Epanechnikov kernel was the best one and the bandwidth was now around 0.4. We can see that this dataset is definitely a little more challenging than the synthetic one that we've been working with before. Here you see the ROC curve and the PR curve are not as optimal as we've seen that so far. But yet again, this is still like a very common picture that we would see. Remember that I, for instance, explained why it's hard to maintain like a high precision if I have these high class imbalances as we see them in our example. So still we can relatively confidently identify anomalies. This concludes our exercises. In the next lesson, we're going to talk about the Curse of Dimensionality. Okay, now that we had the opportunity to work a little bit with the KDE, I hope you all saw that this is a very powerful technique to estimate densities from data. However, this comes at a price, namely that the dependency on the dimensionality of the data is quite unfavorable. There is a famous theorem by Stone, 1982, which actually says that any estimator which is consistent with a class of k-fold differential PDFs has a convergence rate of at most 1 over, then we have n to the k divided by 2k plus d. So we're talking about the sample complexity here, so basically telling you how many samples I need in order to get the error down. And here we see that the dimensionality comes in very unfavorably, because basically I need to take the d square root of the number of samples that I have in order to achieve the same quality as, for instance, for a one-dimensional problem. So in this case, the complexity gets exponentially worse as we increase the dimensionality of the space. Okay, in case that you wonder what consistency is, so we have written it down here. There are several notions of consistency, but we are working with the one where we say that the limit when the data goes to infinity of the density estimate that the KDE gives us and the true density converges to 0 in the infinity norm. So looking at the supremum of all possible differences. This is a very important concept, and I think it's good to have another exercise. All right, in this exercise we want to review the Curse of Dimensionality, and for that we had prepared a little example for you. Here you see the sinusoidal shape that we've already talked about before, only in 3D. Now we get this thing that looks a little bit like a Mexican hat, and you can see that we have again in blue shown the anomalies, and you see these two little yellow dots here, which are the anomalies. So again, it's a little bit more challenging task. Here we have non-convex shapes and we have the anomalies rather close to the nominal points. So what we want to see here is that if we change the dimensionality while keeping the number of examples or the number of samples the same, then we will see that we quickly degenerate the quality of the fit that we get. So meaning that we really need exponentially more examples if we increase the dimensionality. So, okay, let's have a closer look at this example. As you can see, we have this sinusoidal shape evolving in the z direction. spreading out in X and Y direction. All right, so let's see how KDE behaves if we increase the dimensionality successively. I think you can imagine how this will look like if we go into higher dimensions. Then of course we still have the last dimension is where basically this wave evolves and it spreads out in all the other directions. And here we fit this for up to 16 dimensions. And I think the images here that you see, I mean, you see always these are two-dimensional images. They are always cross-sections of the true density. So here above you see we fix the first components all to be 0 and then only look at the last two components. So in the end we always want to see the same shape, this sinusoidal shape that we see in the first image. But as you can see already with dimension 4 starting, these images quickly start to degenerate. So sometimes it's undersmooth, we only see like parts of this W shape, but most of the time it's actually oversmoothed. Remember that we have chosen the bandwidth automatically. And then you see that as soon we go into higher dimensions, in order to keep these points really, or to get these points really to connect, we really need high bandwidths, and this is why we can't find, or this is why we can't model the fine structure in this cross section here. All right, let's talk about robustness. In the beginning, I've already mentioned that robustness is extremely important for us since we have to work with datasets that potentially contain anomalies. Unfortunately, it is the fact that KDE is not really robust against these contaminations, and we will definitely have to take measures against it. One way of measuring robustness is the so-called breakdown point, which is defined as the smallest fraction of my data that I need to change in order to be able to move the estimate arbitrarily far away from the true value. So a classical example that you might know is the sample mean of a data set, which is known to be not very robust, meaning it has a breakdown point of 0. It is enough to change a single sample in the data set in order to move the mean to any value that we want. That means that the breakdown point of the mean is smaller than 1 over n for every natural number n, so it must be 0. What can we do to make our estimates more robust? Well, we can look into methods that have been developed in the context of robust statistics. Here we try to find robust replacements for the sample mean. For instance, the median of means, which splits the dataset into equally sized subsets, x1 to xs, and then computes the mean for each of these, and then takes the median, what you see down below here, as our estimate. So maybe you have already heard that the median itself is more robust than the mean. And the median of means is basically a combination of these two, which will be especially beneficial when we look at the kernel density estimate. Another very classical but also effective method is the so-called M estimation. And it rests on the observation that the sample mean can be described as the solution of an optimization problem, namely the one that tries to find the y that minimizes the squared distance to all the other points in the data set. So this will be the mean. The solution of this equation will be the mean. And M estimation basically replaces this quadratic loss that we have in this function by more robust versions. The most well-known of these more robust loss functions is the so-called Huber loss, which is defined to behave quadratically when we are close to the data point, and then at some point switch to a linear behavior for a given threshold delta. We can even take this to a more extreme loss function. The so-called Hampel loss has basically two thresholds. The one very similar to the Huber loss, where we switch from a quadratic behavior to a linear behavior. But then, as we go further away from the data, at some point we have a second threshold where we switch from a linear behavior to even a constant behavior. So you see that the data points that will be very far off will at some point get some specified fixed loss value. So we would like to apply all these methods for robust mean estimation also for the KDE. But in order to do so, we really need to understand that the kernel density estimate is by itself also a mean. So let's try to understand that. First of all, we need certain properties of the kernel, namely that it's radial and monotonic, where monotonic means that the density is only increasing as we move away from the center, while radial means that the value of the kernel only depends on the distance to the center. So now it makes sense to view the kernel itself not as a function of a single value, but as a function in two arguments. So if you remember how we defined the kernel in general, then we always plugged in the distance between two points. The point that we want to evaluate the density at and one point of our observation. And of course, we can see this also as a function in two arguments where we just plug in x and y and then define it to first compute the distance between them and then plug it into our kernel. So in this way, we can actually see this expression where we fix one of the arguments, say x, in the kernel as a new function in one argument, which always computes this kyx or kxy for all possible inputs. So that means that we're actually working over a vector space of functions, namely the linear span of all the basis vectors phi x that we've defined before. And the operations are, as you would expect, the pointwise addition and the scalar multiplication. So now we want to make a Hilbert space out of this vector space of functions. What we need to do there is to define a scalar product on them. And here we are actually lucky, because if we have a radial and monotonic kernel, we can actually show that just plugging in x and y as the scalar product of phi x and phi y will just work as fine as a scalar product for this space. This has, of course, an advantage compared to the standard scalar product that we would define here, because we can actually compute the value. We call this vector space the reproducing kernel Hilbert space over K. And we can see that in this kernel Hilbert space, our KDE is actually a mean, because the expression that we've seen before to define the density over a data set is actually the mean over the sum of the corresponding basis vectors. So now we are really in a setup where we can say all the results that we know for robust mean estimation also hold for kernel density estimate. So we can directly apply them. And I think it's very good to do this in an exercise. So please work through the corresponding notebook and we see each other again with the solution. So finally, we also had the example of the Huber and the Hampel loss in this notebook. So here again, if you like, you can play a little bit with the values. You can try out to change the thresholds, for instance, and see how this Huber loss looks then like. But this is only just for you to play a little bit more with that. And then finally, we are going to work on an exercise regarding the robustness. All right, in the last exercise of this module, we are going to have a look at robust KDE versions. More precisely, we are going to have a look at our houses dataset and then look what happens if we change the fraction of anomalies that we have in the data and how these robust versions of KDE perform in this case. So please work through the individual cells of this exercise and we see each other again with the solution. Okay, so in this exercise, it was again mostly about observing the behavior that we see. So there was no real task. It was all about running the cells. Again, let's see what we've done. We've defined different algorithms: the standard kernel density estimate, the median of means KDE, the robust KDE with Huber loss, and the robust KDE with Hampel loss. As I said, we are going to use the house prices dataset, and now we are taking again the college area, but as anomaly neighborhood, the Edwards neighborhood. And here we defined the different fractions of anomalies that we're going to look at. And so you see, we're basically working from 1% up to 50%, looking at different values. So the code was all pre-prepared, I just needed to run it. Here you saw the results of the individual runs. And finally, you could create this plot. So looking at the visualization of the results, I think it becomes pretty clear that the Hampel loss consistently outperformed all the other losses. So we can see that although once we started to incorporate anomalies, that all the different estimates had quite a bump in their performance, but still for every fraction that we had, it was the case that the Hampel loss was by far the best working. So I have to say that in this case, you might have better results also with the Huber loss if you would play a bit with the thresholds that we've defined, switching from quadratic to linear behavior. So we just took the standard values here. That might be a reason why in our case the Huber loss performed equivalent to the original KDE. Maybe just the distances were not high enough in order to make a real difference here. Also, it might be mentionable that we also don't quite know why the quality recovered for these high proportions. So the more interesting part is actually the one before that, where we actually see the bump and where the anomaly fractions are actually in the range that we would also expect in realistic scenarios. While there are cases where you even have anomaly fractions up to 20 or maybe even 30%, usually we would expect them to be way below 10%, and this is really the area that you should look at. But still, the results are consistent. Hampel is the one that worked most for all of these cases. All right, that concludes Module 2. So I hope you got a good idea of how anomaly detection via density estimation works. In the next module, we are going to talk about anomaly detection via isolation.